Hello, and welcome to this lesson in quantitative reasoning on equivalent statements. So, I did not create these slides, so let me make sure you see that. All right, so here's what we're going to look at is equivalent statements, and we're going to determine if two statements are equivalent using a truth table. We're going to look at two statements in English, turn them into symbolic statements, and use a truth table to determine if they are equivalent. And we're going to use De Morgan's law to determine if two statements are equivalent. So we can use truth tables to compare two symbolic statements and see if they're equivalent. In order for two statements to be logically equivalent, the final column that shows the output of each statement has to be exactly the same in each row. So for example, this truth table is going to compare if P then Q and if Q then P with the biconditional P if and only if Q. So we've got a compound statement here and another simple statement here, and we want to see if they mean the same thing. So you set up your truth table. Here is your common input columns. Anytime you have two statements, you have 4 rows, and regardless of what we're going to do, these first 2 columns would be the same. Doesn't matter what we're going to do with P and Q, we always start out saying here's all our possible inputs, and here's the order you put them in. You should have that on your notes for your test. So then I do an if P then Q. And what you have to remember about the if P then Q is if P is false, the statement's automatically true because there's no evidence that you made a promise and didn't keep it. P is you promised that if this thing on the left happened, then Q would also happen. If the thing on the left doesn't happen, there's no evidence you were a liar, so it's true. So, for the first row, promise was made, promise was kept, made a true statement. Here, it's like I told my grandson, if you eat your lunch, then you can have a candy bar. He eats his lunch, and then I don't let him have a candy bar. Then he's mad because I didn't keep my promise. False. And the other day, he didn't eat his lunch. So P was false. And if I gave him a candy bar, he wouldn't have been upset. So that would have been, he wouldn't have been calling me a liar. And if I didn't give him a candy bar, he had no right to call me a liar. And I didn't give him a candy bar, by the way. But anyway, so this is the output for the column for if P then Q. So I'm breaking this into parts. I have that in parentheses and I have that in parentheses. So I do a column for each of those. And neither of these use any negations, so I don't need a negation column. I just need a column for the left and a column for the right for each, and I already have that when I write my input column. So the next one is if Q then P. I have to be careful because the order is backwards. For this one, Q is true, P is true. If true, then true is true. Here, Q is false, and P is true. Didn't make a promise. Q is the promise this time. No promise made, so you can't call me a liar. So that's why that's true. Here, Q is true, but P is false. Grandson ate his lunch and I didn't give him a candy bar, so then Nana was a liar. And then false is true. So now I have a column for this and a column for this. I have the left side of this and in a column, and I have the right side. So I take the left side and the right side, and this is the left and this is the right, and I join them with the and statement. The facts for the and statement are two statements joined together with an and are true only when both are true. Any other case will be false. So in this case, the left, I'm going to do this in a different color so you can follow it better. The left is true, the right is true, my answer is true. The left is false. Doesn't even matter what the right is, it's true, the answer is false. As soon as I see a false, it's false. Left is true, right side is false, right side of the end is false, so it's a false. And both sides of the end are true, so I get a true. So that was this statement here. And the question is it equivalent with this statement here? So I'm going to circle that. That's one column I'm interested in for my end. Now, I look for the if and only if. I have to do the if. I have to do the second statement. If and only if means if P is true, Q is true, you get a true statement. If P is false while Q is false, you get a true statement. This means that no matter what one letter is, the other one is the same thing. If they are different with the biconditional, this is called the biconditional, P if and only if Q, then the statement's false. So today is Friday if and only if tomorrow is Saturday. Those both are either true. So today is Friday. So P is true. So Q must be true for that statement to be true. But if today were Thursday and tomorrow were Saturday, what I said was not true. So what you find is the left side is just P, the right side is just Q. When the left and the right match for the biconditional, you get a true. That might be a good way to write this down in your notes. So I look over here. P and Q are the same in the top row, so I get a true. They're different in the second row. They're different in the third row, so both of those are false for the biconditional. P, Q are both false. Now, this gets students confused. All I'm asking, all this says is, give me a true if these two have the same value. They are both false, so yes, that statement is true because the left and the right match for the biconditional. So there's my other output for the statement I'm comparing. And you look row by row. The first row's the same, the second row's the same, third row's the same, fourth row's the same. So these are logically equivalent. On to the next one. Now you can always, I'm moving a little fast, but you can always stop the video, rewind, play it again. Use a truth table to determine which of the following statements are equivalent to not P or Q. So these must be the statements they were interested in. This, and this. So they're going to make a bunch of truth tables. Notice that we have not P in this one. We have not Q in this one. So we're going to first start by making a not P and a not Q, because no matter what your statement is, you want a column that contains what's on the left. You want a column that contains not P and a column that contains what's on the right. So you just are comparing trues and falses with a connective, not trying to do multiple things at once. So for not P or Q, there's the not P or Q, true. They're both false in the second row, you get a false. They're both true in the third row, true. As soon as you get a true, it's true with the or. If P then Q, so I'm looking here, if P then Q, the only false case is the promise was made but not kept. That's the only false case, so that column is filled out with that. This turns it around. If you want to see the reasoning for this, you can go back to the prior slide and back to the prior example. So here for if Q then P, I would have a if true then true. Then I would have an if false then true. And then I would have an if true then false, because the Q is what's on the left. So these second and third columns actually swap when you swap the order of the letters. So that's if Q then P. Now if not P then Q. So there's my not P. And some people like to write out not P here and Q here, just to make sure they're doing things in the right order with the if then, and write the answer in the middle. So not P, anytime the left is false, the if then is true. Now notice, it doesn't matter that this was not P. I took the values of not P and put them here. I don't have to say, oh, wait a minute, not false is true. No, I've already done that. So if false then true is a true, if false then false is a true, doesn't matter. True then true is a true, true then false is my false case, so I have that false. And then in the final column, not Q or P, you're taking, let me do this in green, not Q or P, you're taking these, and if it's an or, as soon as you see a true, you have a true. The only time you get a false is two falses, and that's only that third row. So there's your false, and the others are true. Now, we haven't even done the problem yet. We just confirmed the truth table. So they are asking which of these are equivalent. And I'm going, you need to look and see, okay, so I look at the first column, true, false, true, true. What else has true, false, true, true? Well, this column and this column are equivalent. Is there anything else? Nope, I have trues in all my other second rows, so they're not equivalent. So the two yellows are equivalent. And let's see. True, true, false, true. True, 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 false, true, true. Oh, I have a true, true, false, true here, and a true, true, false, true here. So if P then Q is the same as not P or Q. So if you have trouble with the if then, you can always rewrite it in this order and negate the left, keep the right. We talked about that in class. And if Q then not P is equivalent to not Q then P, and neither of these are equivalent to not P, if not P then Q. But we have the yellows are equivalent to each other and the pinks are equivalent because the final column is exactly the same in every row. Okay. So this is asking us to construct a truth table to determine if any of these are the same. Well, I'm going to tell you that I can tell just because I know forms that this is not going to be the same as anything else. But let's move on. They made our truth table. R, P. I do not like this. I like to do them in alphabetical order. This is not some, I would have set this up PR, but if your text gives you a problem like this, just follow through with what they have, with the columns the way they have them. If they give you these two columns, just keep them that way. I would have put them in alphabetical order. P would have been first. And that's more standard, I think. So because if I go back to look at all those statements, I had a not R and I have a not P. So I just make my not R and my not P up front. Then I have R or P, true, 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 false. If not R, then P. Not R is false in the first two rows, so this is automatically true. If the left side of an if then is false, it's automatically true. And then I have a true then false, true then false. Oh, look at that. I have a true. No, this is a mistake. I have a not R, then P is a true then true. This should be a true. And that should be a false. That's why I'm doing this one. Sometimes the book has mistakes. There's only one false one there. Then, in this column, R or not R, that's a tautology. You're saying true or false or true. Those are the two choices, because R can either be true or false. And the negation of R is the opposite, so you're always going to get trues because the or only needs one true. Not R and not P both need to be true. I look at not R, I look at not P. Let's see, false, false, false. The only row that's true is the bottom, and the rest will be false. That's what we have. Now, this last one here takes, I'm going to label that with a 1 and label that with a 2. 1 or 2. And the funny thing about 2 is it was always true. And here I have an or, so this side is always true. It's an or, so you get all trues here. So far you have this and this are equivalent statements. Now, if I do the biconditional from R to R or P, I do not, I do have R or P here. Let me do a different color. So there's R or P here, and there's R, and I want to know when they match. True, 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 true. Okay, so the first two rows, R and P are the same, so my biconditional is going to be true. The third row, I have a false. The last row, they're both false, but since they match, it's true. So I get true, true, false, true. The only issue is here where they're different. So I get a false. So I look at this, true, true, false, true. That does not look like any of my other statements, but it does look like it would be if R then P. But they didn't ask us about that. But it's definitely not this one. This one's true, true, false, true, false. False, 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 true. This one's actually the opposite of this one. So to make observations about whether statements are equivalent or opposite or tautologies, you make a truth table. So now we're going to start with statements given in English. The question is, compare the statement, Paul likes dogs, with Paul does not dislike dogs. Remember that old double negative? I'm not going to do this means I am going to do this. So first you make a truth table for Paul likes dogs. So statement P is Paul likes dogs. Paul does not dislike dogs is the same thing. Paul does not dislike dogs. He does not like dogs. When you do not P, you get P. They should be exactly the same thing. This is Paul dislikes dogs. Paul does not dislike. So they did the Paul dislikes dogs first, and then they did the negation of it. So the double negative comes out to be the same as making the statement there. Let me see what the next example brings us. It will rain today and the baseball game won't be canceled. It will rain today and the baseball game will be canceled. The baseball game won't be canceled if it doesn't rain today. If it does not, it is not true. So that is not true. Should tell you need parentheses around your symbols when you make them. So we're going to let P be it won't rain today and Q be the baseball game will be canceled. It will not rain today. So it will rain today. See, I would have made P it will rain today. But they made it it won't. So it will rain today will be not P, because it won't rain today is stated as P. I would have stated P as it will rain today and not P as it won't rain today. But so use a truth table. So when we convert these English statements, it will rain today is not P. The baseball game won't be canceled. Well, Q is the baseball game will be canceled. So this is not P and not Q. Want to make a statement for that. It will rain today is not P, and the baseball game will be canceled, not P and Q. The baseball game won't be canceled if it doesn't rain today. So this is an if then. If it does not rain today, so that's P, won't rain today. If it won't rain today, then the baseball game won't be canceled, not Q. And it is not true that the baseball game won't be canceled. That's not Q, because Q is the baseball game will be canceled. If it doesn't rain today, if it doesn't rain today, this is tricky. If it doesn't rain today, it won't rain today is P, then not Q. The if it doesn't rain today, then the baseball game will be canceled is the way you say that. It's in the wrong order. You got to get used to that. That's why math statements are so much easier to interpret than English language, because we use all kinds of different words and orders and things to mean the same thing in English. But math, it's kind of always the same. If I see if P, then not Q, there's no doubting the order of that. So let's see what they said we were proving. If P, then not Q. P, then not Q, not P and Q. And not P and not Q. Okay. So this is how you would set up your truth table for all of these. Not P and not Q. Be here. I'm not going to go. So you have not P's and not Q, so you make them here. If you go through this, you can stop the video and look at this and confirm that these are right. Not P and Q. Well, not P is false, but Q is true. And then Q is true. And Q is false, and not P is true. So you only get the one true here. That seems correct. If P, then not Q. So the false case should be the first one, and the rest of them are true. Because true, then true is a true, and then P is false. The left side is false, and then if then, you're automatically ever true. They call that vacuously true. Now, what you notice here is this is the inside of that. So they're just asking me to write the opposite of each thing I wrote here. That's the way you break this down. You're breaking this down. You do the inside first. That's right there. And then you do that after you find the value of this. You now just write its opposite. And then P and Q is typically true, false, false, false. So are any of these equivalent? So I wasn't looking. So false, true, true, true. I don't see any of those. So I get false, 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 true. False, false, true, false. I don't see anything like that. False, true, true, true. So it looks like this and this are the two equivalent statements. Now, there might have been no equivalent statements, but that's how you can sort out a whole bunch of words to see which mean the same thing. Lawyers do this all the time. Maybe not in symbols like this, but they do this all the time. All right, so that's the final. You can stop that if you want to read that slide. I don't need to read it to you. The next thing is De Morgan's laws. De Morgan's laws show us a pattern for writing an and with a negation outside of it as an or, distributing the negation. It's kind of like in algebra. When you had negative x plus y and you distributed that negative, you're distributing a negative 1 through, it comes out negative x minus y, or negative x kind of plus a negative y. Maybe that's not exactly a full analogy, but you can't just negate the x. There were rules for doing this, okay? It's not, the analogy doesn't quite hold. But look, I want to bring this negation inside. So the P was on the left and the Q was on the right. I negate the left, I negate the right, and I change the or to an and. If my negation's outside of an or, I again negate the left, negate the right, change the and to an or on the top. I change the or to an and in the bottom. So that means they are equivalent, and wherever I have this written, I can write this instead, or wherever I have this written, I can write this instead. That's the utility of equivalence in math. Let me go to the next slide. So use De Morgan's laws to determine which of the following are equivalent. So I have the negation of R and T, and the negation of R or the negation of T. So did I negate the left and the right and change the sign? Yes, I did. Those are equivalent. So what if I start with this? Not P and not Q. And I want to put that negation outside. I have to write the opposite. So I had not P, so I write that as a P. I had not Q. And then flip the sign. It should be this. Not P. Oh, so you see, it didn't flip the sign. So that's not a negation. P and Q and not P and not Q. Those are not going to be the same because I just showed you that that's that. P or Q, if you wanted to write a negation, you'd have to have the negation of not P and not Q. You negate P and Q, not P, or not, the negation of not P. You change the sign on each, and you flip the sign in the middle and put the negation outside. I don't have that. Scott doesn't like either flying or driving. So Scott doesn't like flying, not P. Scott doesn't like driving, not Q. So Scott likes flying is P. Scott likes driving is Q. So I write that. And Scott doesn't like flying and doesn't like driving. Doesn't like flying and doesn't like, sorry, this was or. This first one is an or. They're definitely not the same. You can't just switch that. Okay? So these are not equivalent either, I believe, is what they'll tell us. Oh, they interpreted it differently. They said Scott doesn't like either flying or driving. It should have been done like that. Sorry, I missed that. Okay, so Scott doesn't like either flying or driving. Scott likes flying as P. Scott likes driving as Q. They say that goes in here and this goes outside, in which case it would be the same as Scott doesn't like flying and Scott doesn't like driving. Sorry, that word either does imply those parentheses too. I missed that. All right. So, again, use De Morgan's laws to determine. So, I'm distributing. First of all, I have an or. I should have an and. I negated the left. I negated the right. Those are equivalent. Doesn't matter what the letters are. Here, I start with a not. I start with a not. So, I would have to, in parentheses, put just a P and just a Q and flip the sign. This is not in parentheses. These two are not the same. If you made the truth tables for them, you would not get the same thing. So that is not equivalent. This one is and two is not. So hopefully those examples will help you, and that's what I have for equivalence. See you in class.